All right, so in the last portion of today's lecture, we're going to shift gears a little bit, and instead of talking about visualizing filters, we'll actually talk about using some similar techniques to actually modify images. So before, we wanted to ask this question. Given a particular picture, what is channel 17 in layer con 5 looking at in this picture? Or, in general, what is channel 17 in layer con 5 responsive to? Whereas now we're going to pose a slightly different question. We're going to say, given this picture, what would it look like if it were a Monet painting? Okay, now you might say these are just like totally different things. Like why is this even on the same slide? Well, the intuition is that Monet paintings have particular feature distributions. And those feature distributions are reflected by the activations of units in a convnet. So if we can somehow transport these distributions over to other images, maybe we can turn an image like a photograph into an image that looks like a Monet painting by exaggerating the degree to which it activates features that are also activated in Monet paintings. So the same kind of techniques that we use to optimize images with respect to activations of classes and features, we're going to use to modify images to make them resemble other images. Okay, so the first technique I'm going to talk about that's kind of doing something along these lines is a technique called deep dream. Intuitively, you can think of what deep dream as doing as looking for patterns in clouds. If you've ever been outside on a cloudy day, you look up at the sky and you see the clouds drift past. And you might say, well, that cloud over there, maybe it looks a little bit like a dog. That cloud over there resembles a fish. Let's see if we can get a convnet to do basically that. We're going to ask our convnet whether it sees something in the image and then exaggerate that feature so that it sees more of it. So maybe our convnet will look at this picture and will say, okay, I don't really know what it is. This doesn't really correspond to any of the classes I've seen, but it looks kind of like a dog. Like my dog probability is like a little higher than my other probabilities. So then can I just modify the image to increase that probability, to increase that activation? And where is the dog? And can the convnet show you where it is? So thinking back to this picture of the cat with the eyes, here you might imagine that making the eyes more blue will make this more cat-like. But let's apply it to an image that doesn't have an easily recognizable class, like this picture of clouds. Well, here's what Deep Dream will do with the inception network. And the procedure is basically like this. Pick a layer in your convnet, run a forward pass to compute the activations at that layer, set your delta for backprop to be equal to the activations at that layer, and then backprop and apply the gradient. So essentially it's saying whatever units are activated at that layer, activate them more. It's kind of a funny procedure, but the results are actually quite striking. So if we look closely at the image on the right, viewed from far away, it just looks like the same clouds as on the left. But if you look at it up close, you start seeing some objects pop up in the clouds. So here are those objects zoomed in. You can see that maybe some of them look a little bit like some kind of pufferfish or maybe a snail. So it's trying to essentially hallucinate things that it already sees a little bit of in those clouds and basically accentuate them more so that they're more visible. All right. So the procedure for implementing this is actually very, very simple. This is some code. This is from slides by Andrei Karpathy. And what the code is basically doing is it first sets the objective to be the activations at the layer. So that's what the bit highlighted in red says. It's just run your forward pass, figure out the activations, and set the derivative of your loss to be those activations. So that's the same as setting the objective to be the sum of the activations. And then when it actually applies a gradient step, what it's going to do is it's going to apply a little bit of jitter to the image. So that's the bit that's highlighted in blue. Then it's going to run a forward pass, compute the subjective, the one that sets the delta to be the activations, and then run a backward pass. So that's just backpropagation. And then it will apply that gradient to the image, there's a little bit of normalization just to avoid any issues due to overall scale. It will apply that to the image, and then it will jitter a little bit more. So what the jittering is doing intuitively is just preventing this optimizer from doing crazy things to a particular pixel. It serves the same role as R of X from before. It's essentially a regularizer to promote this looking like a natural image. If you don't use this kind of jitter, what will happen is that you'll basically get a crazy image where the pixels get minute and nonsensical modifications that essentially fool the network into maximally activating some class. With this jitter, what it's doing is it shifts the image a little bit, applies the gradient, and then shifts it back. And that just makes sure that this exploitation problem is not too severe. Okay, so it's a very simple procedure. And it's essentially doing the same thing that we were doing before, only S of X now is just the basically the squared activations at that layer, because the derivative of the squared activations is just the activations themselves. So here are some images actually generated by Deep Dream. Of course, this starts with particular pictures and then modifies those pictures. And you can kind of guess as to what those pictures were. So in the top right, this was Starry Night by Van Gogh. In the bottom right, it was a photograph of some sheep in a field. But the network clearly makes some pretty drastic modifications to these images. For example, you can see that for the image on the left, it actually inserted some eyes, quite a few eyes that were not there to begin with. In the sheep image on the lower right, it did a few things that were kind of nutty, like adding lots of legs to the sheep, because I guess some of the bottom parts of the sheep looked a little bit like animals, so it put more animals in there. It also changed the sheep's nose into a dog nose. For Starry Night, it appears to have put in a large number of wheeled vehicles into the picture. So it's kind of doing this crazy sort of hallucinatory stuff, and you can play around with it yourself if you go to that URL on the slide. Now you could ask at this point, like, well, what is this good for? Okay, mostly entertainment, mostly a little bit of kind of artistic license. You can get some crazy images out of ConvNets. But you can actually repurpose some of these ideas to do things that are a little bit more maybe useful, a little bit more pragmatic. So here's another idea that's closely related. Instead of exaggerating the features in a single image, what if we make the features of one image look more like the features in another image? For example, what if we take a painting and we somehow extract its style by looking at the statistics of the features in that painting? Maybe that style is represented by the relationships between features, like which features tend to occur closely together. Maybe there are lots of angles and lots of straight lines, but not a lot of curvy things, right? That might be one stylistic aspect of the picture. And then we take another picture, like a photograph, and we pull out its content. Maybe the content is more reflected by the particular position of features in space, where things are in the picture. For example, where are the corners or the edges or the curves? And if you combine the relationship represented by style with the spatial positions represented by content, maybe you will get a modified version of the photograph that reflects the style in the painting. So maybe you'll get a picture of Gandalf in the style of a particular modern painting. Does this really work? Well, surprisingly enough, yes. To talk about how to make it work, the most important thing we have to talk about is how do we quantify style? And it turns out there's actually a fairly simple way to do this in terms of ConvNet activations. All right. So let's say that we have this painting and we run it through a convolutional network like VGG. And we look at a particular layer in VGG. We're actually going to look at many different layers, but let's start with one layer. The different filters at that layer reflect particular visual patterns. Lower level filters might reflect simple patterns like edges. Higher level filters might reflect more elaborate patterns like swirly things and curves and straight lines and angles and so on. Now, when we're trying to quantify style, we're going to try to discard spatial information. We don't care very much about where the particular curves and angles happen. We care more about which ones happen and how they relate to one another. So what we can do is we can pull out all the different filters at a particular location, and each of those filters, let's say there's 5 of them, they'll correspond to different patterns. Maybe one of them corresponds to circles, another one corresponds to these spirally things, and so on. In general, we'd have like maybe 64 or 256 filters. Here I have 5 just to make it easier to draw. And then we're going to ask this question. Which features tend to co-occur? For example, could we say something like, in this particular style, at a given location, if you see a circular thing, you're also likely to see some swirly thing. So this is a style of circles being near swirly things. So each time we see a straight line, we also see this particular texture. Or each time we see a curve, we always get flat shading. Or each time we see a swirly bit, we also see a corner. Okay? These are kind of stylistic properties, independently of where in the image they are. So can we quantify this kind of relationship? One of the ways we can quantify it is by building a feature covariance. So for two features, K and M, so features here are filters, for two different filters, K and M, at a particular layer, you can compute the expected value of their product. The expectation is taken over different positions in an image. So this is for a single image, for a single painting. Go over every position in your activation map, and over all the positions, average together the product of those two features. And if the features tend to occur together, then their products will be very large. If they rarely occur together, meaning that if one of them is non-zero, the other one is usually 0, then their products will be very small, they'll be close to 0. So features that occur together will have large products, features that don't occur together will have very small products. And you can build a matrix called the Gram matrix, where the entry Km in this matrix is just the covariance of filter K and filter M. And it turns out that this Gram matrix is a very effective way to quantify the style in a picture. Now you get one of these matrices for every layer. The dimensionality of the matrix is just the dimensionality of the number of channels. So it's channels by channels. It's independent of the resolution of that activation map. Because remember, you're averaging over all the XY positions. So this discards all spatial information and preserves the co-occurrence of features. Notions like every time there's a straight line, you also see this texture. If there's a feature for straight line and a feature for that texture, you'd expect their product to be large if they occur together and small if they rarely occur together. So if features have this covariance, then we have, in some sense, the right style. This might seem surprising, but it actually turns out to work if you're a little bit careful about which layers to select. So this Gram matrix is going to be calculated for the source image, for the image that is meant to represent the style. And then we're going to construct a new image by optimizing two objectives, a style objective and a content objective. So the style objective will be based on this Gram matrix. So let's say that GL is the source image Gram matrix at layer L. And AL of X is the Gram matrix of the new image at layer L. And it's a function of X because as you change the image, you change the corresponding Gram matrix. And then we can write down a loss, a style loss, that sums over all the layers and then sums over all pairs of features at that layer. And it's just the square difference between the entry in G of L and the entry in A of L of X. And each layer is weighted by a weight WL. And this weight actually has to be chosen somewhat carefully because you have to prioritize the relative contribution to the desired style of different levels of abstraction. Remember back when we visualized the filters at different layers. You could see that higher layer filters tend to be more holistic. They tend to reflect complete objects, whereas lower layer filters correspond to more geometric detail. So depending on whether you want to transfer style in a more higher order way by picking out similar looking objects or in a lower order way by picking out similar finer geometric detail, that should affect how you pick your weights WL. And of course in practice there's a little bit of artistry in selecting those weights properly. But if you select them properly, then you can get L style of X to actually quantify the degree of similarity between the style of image X and the style of the image that was used to form that original Gram matrix. Okay, so now to instantiate this, we have to just design an objective for content. And content in some ways should be the opposite. It should mainly focus on preserving spatial positions, like where those features are located, instead of looking at relationships between features. So it turns out that a very simple way to quantify content is to just match the features in the content image. So if Fijk L is the value of filter K at position ij in layer L, then you can just sum over all positions and sum over all filters and take the square difference between those activations. Now, notice a few things about L content that are very different from L style. L content is for a specific layer. It's not summing over all layers. So here you would select a layer that you consider to be reflective of content. And again, that choice is actually quite delicate. And then you would preserve the locational information. So you would actually match the features at position ij to the content image features at that same position. So you want the positions to line up. Whereas for style, you wanted the opposite. You wanted to throw out the positions. So compare this to the style loss. The style loss doesn't have ij in it at all. Ij has already been summed out when we computed the gram matrix for the source image and the target image. And then the complete image is just formed by running back propagation with L style and L content. Okay, so this is basically the procedure. This is the procedure that we can use to take two images, one representing style, one representing content. We match the gram matrix to the gram matrix of the style image, and we match the feature activations at particular positions to their corresponding activations in the content image. So let's look at what this does. It's actually pretty remarkable, the kind of fidelity that you can get with this approach. So at the top I have the basic equations just to remind you. And this is from the paper by Geddes et al. Called A Neural Algorithm of Artistic Style. They're going to take the photograph in the top left, this kind of canal side cityscape, and then they're going to take different paintings. The painting that they're taking is shown in the small inset in the lower left. And the larger picture shows what happens if you take the content in the photograph and the style from the painting. And you can see that it actually does some pretty remarkable things. For example, for the Starry Night picture in image C, it actually puts in those little swirls that are not actually even present in the original photograph. But overall, it preserves the general geometry of the buildings, the side of the canal, and so on. Interestingly enough, it even stylizes the reflection of the houses in the canal. For the screen, for the second row, second column, it actually introduces some additional details. So the buildings further in the background actually get replaced with this kind of swirly skyscape in the original painting. But on the right side, the buildings are still there. So it sort of becomes a sort of amalgamation of the painting and the original photograph. The canal, for example, seems to have been removed and replaced by a bridge because the bridge is such a prominent feature in the original painting. The geometric details are not necessarily preserved, so in the case of the more abstract paintings at the bottom, many of the geometric details are actually eliminated. And that's because the style in those paintings just does not preserve geometric detail. So it's pretty remarkable that this really simple way of quantifying style in terms of the gram matrix of features in a content actually produces some meaningful results. You can play with this yourself. There's a website called deepart.io that allows you to apply styles to photographs. And these are some actual photographs that were stylized in different ways. This is from Andrej Karpathy's slides. So to summarize, we talked about how we can visualize what different filters in a content do by using their gradients. And we can further use those gradients to actually optimize features to maximally accentuate those filters. And when we optimize images to maximally accentuate those features, we can turn that into actually algorithms for generating new pictures and generating pictures that have some artistic properties and even separating style and content.